Hello students, in this video we will recall some organic reactions in the haloalkane chapter. Question number 1. Halo compound is given, write down its E1 mechanism and write down the major product here. What does E stand for? E stands for elimination. E stands for elimination. Stand for elimination. There are two types, E1 and E2. E1 involves carbocation mechanism, just like a SN1 mechanism. Elimination reaction is also called as the dehydrohalogenation reaction. Dehydrohalogenation reaction. Okay. Now, what I do is I have to remove this halogen atom and form one carbocation. It can be primary carbocation, secondary carbocation, tertiary carbocation. Right? So let me remove that bromine atom. So we'll get CH3, 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 then CH plus, then CH3. This is a secondary carbocation. This is a secondary carbocation. Check whether we can have the tertiary carbocation. We can have tertiary carbocation provided this methyl group is going to the carbocation here. That means we cannot have now CH3, CH3. This carbon is positively charged. Then CH3 has gone here. Then CH3. Now this carbon atom is attached to three more carbon atom. This is a tertiary carbocation. This is a tertiary carbocation. Compare stability of secondary and tertiary. Tertiary is more stable. Therefore, we have to write down the product with respect to tertiary carbocation. Again, there are two possibilities here. Okay, I have to remove hydrogen either from this carbon atom or from this carbon atom, neighboring carbon atom. Dehydrohalogenation means removal of hydrogen and bromine from the neighboring carbon atom. So let me write both the possibilities. So it becomes CH2, then CH3, then CH3 attached to one more CH3. We'll get alkene, correct? One more alkene is also possible. CH3, CH3, double bond, remove hydrogen from here. So CH3 and CH3. The valence of carbon is 4, satisfied. Now we have got two products, A and B. Now there is one rule known as the Zeitgeist Rule. According to Zeitgeist Rule, during dehydrohalogenation, that alkene is formed which contain more number of alkyl groups on the doubly bonded carbon atom. So second alkene, this alkene contains more number of alkyl groups. Therefore, this is the major product and more stable product. So it is a more stable alkene. This structure can be written as carbon-carbon double bond you have got. And each double bonded carbon atom attached to methyl group can be written like this. Therefore, answer is option number B. Right? Question number 2. To the given halo compound containing a chlorine atom and the bromine atom, treat it with the K plus, SH minus. It is like a K plus, OH minus. Assume it is aqueous now. Okay, and you write on the major product. Now remember, here this is a nucleophile. OH minus, SH minus is a nucleophile. Nucleophile attack the carbon atom containing halogen. There are two types of carbon atom attached to the halogen. One is a sp3 carbon atom. The next one is a benzene ring carbon atom, sp2 carbon atom. It is easy to attack the sp3 carbon atom. Suppose halogen is attached to the benzene haloarine group. Nucleophilic substitution in haloarine is not possible. One of the reason is a resonance effect. Therefore, we can remove the halogen which is there on the sp3 carbon atom, that is on the alkyl group. Okay. Therefore, I can write the product benzene ring attached to one more benzene ring. Then CH2, this halogen can be easily removed. Introduce SH now. Okay, nucleophile. And bromine atom is not replaced because halogen directly attached to benzene. Therefore, answer is option number C. Right? Question number 3. Given compound is treated as NBS followed by K plus SH minus. Now you know that SH minus is a nucleophile now. What is the NBS? NBS stands for N-bromo. N-bromo. Bromine atom attached to nitrogen atom. N-bromo. Succinamide. N-bromo succinamide. Now what is the use of this one? This one is used for allylic bromination. Allylic bromination. Allylic bromination, and it brings about free radical mechanism. Free radical mechanism. Now what is a allylic bromination? Suppose I got carbon-carbon double bond. The next carbon is called as the allylic carbon atom, and hydrogen attached to that one is allylic hydrogen. Therefore, this hydrogen can be removed. We can introduce a bromine atom from N-bromo succinamide. So let me write on this given compound to begin with. Benzene ring attached to the iodine. Then now we have got a CH3. I'll make CH2. Double bond is in the benzene. Next carbon is a allylic carbon. Introduce a bromine atom. This is known as the allylic bromination. Then followed by K plus SH minus. SH minus the nucleophile. There are two types of the halogen. One halogen attached to the sp3 carbon atom. Another halogen attached to sp2 carbon atom. Now which halogen can be removed? Which is attached to the sp3 carbon atom, remove. So therefore I can get a product benzene ring attached to the iodine, then CH2 now attaches to the SH, right? So this compound is there in option number C. So we have got answer option number C, right? Question number 4, numerical. How many stereoisomers can be drawn from the following molecule? Stereoisomerism is of two types. One is known as the geometrical isomerism, and geometrical isomerism is also known as the cis-trans isomerism. There are two isomers, cis and trans isomers. Next one is the optical isomerism. Optical isomerism. For the given compound, we can have dextrorotatory and levorotatory. Now, what is the condition for geometrical isomerism? There must be carbon-carbon double bond. Each carbon-carbon double bond should be attached to. Each double bonded carbon atom should be attached to two different groups. Okay, and groups can be repeated on the neighboring carbon atom. For optical isomerism, there should be chiral carbon atom. What is chiral carbon atom? Each chiral carbon atom should be attached to four different groups, maybe P, Q, R, S. Groups should not repeat. Now here we have got carbon-carbon double bond. We can write cis and trans. So let me write on cis first. Okay. So we have got carbon-carbon double bond. So let me write on hydrogen on the double bond carbon atom. Then remaining is a CH2 group. Then we have got a CH3. Here, this side we have got hydrogen attached. Then we have got a CH2. Then C. I'll split this one H, Cl, and CH3. So I can write here one chiral carbon atom. So I can also write now trans isomer, that is a carbon-carbon double bond. Now hydrogen should be there on the opposite sides. If the similar groups are on the same side, cis. If they are on the opposite side, trans. Then the remaining group, that is a CH3, then a CH2. Here we have got a CH2, then a CH, CH3, and a Cl. This is the asymmetric carbon atom. Now this cis can have dextro and levorotatory. How many are possible? That is given by the formula 2 to the power n. N stands for the chiral carbon atom. 2 to the power. How many chiral carbon atoms are there? Only one here. To the power 1. That is equal to 2. So under cis, we have got one dextrorotatory cis. Other one is the levorotatory cis. Here, this is a trans. How many are possible? Trans 2 to the power n, which is equal to 2 to the power 1 chiral carbon atom 2. So here also trans dextrorotatory, trans levorotatory. Therefore, cis 2 isomers plus trans 2 isomers, altogether 4 isomers are possible. So, since it is a numerical type question, we should write the answer 4.00. Right? Question number 5. Given compound is treated with one equivalent of, they are given NaOR is a Na plus OR minus, means this can act as a nucleophile. Okay. So let me write down the given molecule. So we have to begin with benzene ring attached to the CH2Cl they are given. Then iodine is directly attached to the benzene. Then we make use of sodium alkoxide. Na plus RO minus is the alkoxide. Nucleophile. Nucleophile can attack the carbon atom containing halogen. This carbon atom is sp3 hybridized, and this carbon atom is sp2 hybridized. Easy to remove halogen from the sp3 carbon atom. So nucleophile attacks the sp3 carbon atom to give benzene ring attached to the CH2OR. Then we have got iodine atom. Now this is like this: Rx reacting with the Na plus OR minus to give ROR plus NaX. We can recall this reaction as the Williamson's reaction. This is a Williamson's ether synthesis reaction. Therefore, answer is option number. Now, where the answer? We can find out option number C is the answer. Answer is A, not C. Okay. So for this question, answer is option number A. So we have to attach RO minus here, right? Question number 6. There is a halo compound and treated with the aluminium chloride anhydrous. Remember, aluminum chloride we are using in a Friedel-Crafts reaction. We use in a Friedel-Crafts reaction. Suppose I write CH3Cl, okay, and treat with the aluminium chloride. What will happen? Aluminium chloride, being a Lewis acid, can take up chlorine atom and it gives CH3 plus carbocation, and will get AlCl4 minus, which is studied in the mechanism like for benzene alkylation and acylation reaction. Now what will happen in this case? So let me write in detail. So we have got a benzene ring, attach the methoxy CH3O. Then we have got 1, 2, 3, 4 carbon. Then we have got a CH2Cl. Okay. Treat with the aluminium chloride. So it will take up chlorine atom. Okay. To give benzene ring attached to the OCH3. Then 1, 2, 3 methyl group. Then CH2 plus. This is a primary carbocation. This is a primary carbocation because this carbon is attached to only one carbon directly. Can we produce a secondary? We can produce. How to produce secondaries here? We have got hydrogen and we have methyl. Suppose I shift this methyl group, then I get a secondary carbocation. Suppose I shift this hydrogen to the carbo group, so I'll get a tertiary carbocation. I'll get a tertiary carbocation. Tertiary carbocation. So let me do that. And that shift is called as 1,2 hydride shift, H shift. Hydride shift. So let me write down. So benzene ring now attach the O CH3 methoxy group. Then so 1, 2, 3, right? Methyl group is there. Hydrogen is gone from here. Positive charge. Then becomes CH3. Okay. So now I will simplify this structure. I'll rotate this structure like this. Benzene ring. Let me write on in terms of double bond, single bond. then OCH3 attached, then carbon 1, carbon 2, carbon 3, attach the methyl and positive charge. Benzene is electron rich. It can attack. Benzene can attack the electrophile. Electrophile is positively charged. It can form new bond between benzene and that carbocation. So I can write now. So bond is broken. These two double bonds are there. Then we have got OCH3. Then we have got 1, 2, 3 attaches to the benzene. Then 2 methyl groups are attached here. Okay. Now, so here we have got hydrogen. This hydrogen is there. So this hydrogen is here. Okay. And but this gets a positive charge. Gets a positive charge. So how to neutralize that one? So loss of the proton to give final structure. So we have got now benzene attached to the OCH3. Then we have got 5-membered ring, and the 5-membered ring here. This position we have got methyl groups. Okay. So which one is matching now? So matching one is we have got actually B is the answer, but here structure is missing. Then the structure, this should have been OCH3. This is the answer. B is the answer. Okay. Question number 7. The major product in the dehydrohalogenation of 3-bromo 2,2 dimethyl butane. Let me write down the structure of the given reactant. Butane, we have got 1, 2, 3, 4 carbon atom. On third carbon atom, bromine is there. And on second carbon atom, dimethyl groups are there, CH3 and CH3. Okay. Then remaining valency should be satisfied by hydrogen atom. Here it is a hydrogen atom. Here there is one hydrogen atom. Yeah. What is the dehydrohalogenation reaction? Removal of hydrogen and bromine from the neighboring carbon atom. Now, first we'll remove the Br atom. Okay. Br should be removed as Br minus now. So we left with the CH3. Tertiary butyl group is there. Tertiary butyl group. Attach to the CH plus now. There is a shortage of one bond, then CH3. Now, there is a carbocation. This carbon is attached to 2 more carbon atoms directly. Secondary carbocation. Check whether we can have tertiary carbocation from this. We can get tertiary carbocation provided this methyl group is shifted to the immediate carbon atom. And this is known as the 1,2 methyl shift. So I can write now CH3, C, positive charge shifted. Then CH3 is remaining, then C, H, new CH3, then CH3. Now see this one. This carbon attached to 3 more carbon atoms. Therefore, this is the tertiary carbocation. And the tertiary carbocation is more stable. It is more stable compared to secondary, compared to primary. Now, remove hydrogen. There are 2 possibilities. Okay. I can remove hydrogen from here or from here. Okay. So you also remember Zeitgeist rule. Remember Zeitgeist rule. I should get a more stable alkene. I should get an alkene where there should be more number of alkyl groups on the double bonded carbon atom. So let me remove from this carbon atom. Or we have to remove hydrogen from that carbon, neighboring carbon atom, which contain lesser number of hydrogen to give more substituted alkene. Therefore, we'll get a final compound alkene as a CH3. 2 CH3s are attached to the carbon atom. Then we have got a double bond C, CH3 and a CH3. Okay. Structure is not given, but the IUPAC names are given. So carbon number 1, carbon number 2, carbon number 3, carbon number 4. So it is a butene. Which butene? Butene. Double bond is there on the second carbon atom. Then there are methyl groups CH3 and CH3 on second and third. So it is a 2,3 dimethyl, 2,3 dimethyl butene. That is option number C. Right? So you have to follow the Zeitgeist rule and get more stable alkene. Question number 8. Among the following, which statement is incorrect? So I'll start with the option number D. Okay, option number D. See there, they are given here alkyl group and halogen attached. Here aqueous KH is there, K plus and OH minus is there. So you know that it's a nucleophile. Okay, nucleophile can attack the sp3 carbon atom. Therefore, I should get product. Cyclohexane ring attaches to the CH2, then attach the OH. But what they are given here, they are given alkene, which is a dehydrogenated product. To get this one, I should have alcoholic KOH. Alcoholic KOH is known as the dehydrohalogenation, brings about elimination reaction to give alkene. Therefore, option number D is the incorrect. Actual answer, I should get alcohol. This is the answer. So option number D. Okay. Answer is option number D, incorrect statement. What about the other statement? See, they are given in the beginning, we have got CH3, COOH, and they have said that does not respond to the haloform reaction. Okay, that means halogen and alkali should be there. Now, which compound can answer haloform reaction? All those compounds containing methyl keto group can answer iodoform reaction. And any other R group should be there here, right? Any other R group. This R group can be hydrogen, R group can be alkyl group, or it can be aryl group. Okay, it can be aryl group. Okay, there should be methyl keto group to answer iodoform reaction. Next one, here it is a CH2 double bond CH, single bond CH2, given like this. CH2 double bond CH, single bond, iodide group is there. And this is that it undergoes a Cannizaro's reaction. Okay, it will undergo Cannizaro's reaction. Now you can see that alpha carbon is there, alpha hydrogen is also there. But this alpha hydrogen is attached to sp2 carbon atom, cannot be removed easily by the alkali. Therefore, it does not undergo aldol reaction. Instead, it undergo Cannizaro's reaction. Okay. Option number C. Given compound contains 3 chlorine atoms like this on the same carbonate, then CHO is there. Okay. Now here the compound does not undergo Cannizaro's reaction they mentioned. Now this is alpha carbon atom. Hydrogens are not there, right? Should undergo Cannizaro, but the given does not undergo Cannizaro, which means okay, some other reaction taking place. Option should be only one. Okay. Now what will happen here? This is one of the intermediate formed during haloform reaction. This is the intermediate form. What will happen here? See here. All these hydrogen which are there on the okay alpha carbon atom, they can be replaced by the halogen. So this is one of the intermediate that is formed. Again, what will happen? The alkali attack the CH2 group. It gives finally CHCl3 and we'll get the salt, sodium salt of the formic acid. So statement A is correct, statement B is correct, statement C is also correct, but statement D is wrong, incorrect statement. For this question, answer is option number D. Question number 9, numerical type question. How many statements are correct? Okay. Option statement A. Nucleophile makes rare attack in SN2 reaction and expels the leaving group from the front. Okay. Rare means a backside attack. Okay. In the SN2 mechanism, nucleophile attack the carbon atom opposite to that of the halogen group. It is a correct statement. It is a correct statement. Option number 2 there. The compound CH3O CH double bond CH2 adds to HBr, H plus and Br minus according to anti-Markovnikov's rule. First we'll write down Markovnikov's rule. What is Markovnikov's rule? H plus should go to that carbon of the double bond containing more number of hydrogen. Br should go to the other carbon containing lesser number of hydrogen atom. Remember, it follows a carbocation mechanism, and the carbocation form should be stable. Okay, that is, first I'll add H plus, so you get a CH3O CH single bond CH3. This is the carbocation. This carbocation is stabilized by providing electron from the electron donating group. So it can donate electrons. OCH3 electron donating group, or also lone pair can be involved here to give electrons. So this is a stable actually. This is a stable. Okay. Suppose I write other way around, like anti-Markovnikov's rule. Anti-Markovnikov's rule. Okay. CH3O CH2 I'll write here. Then CH2 plus. This is also carbocation, but this carbocation is connected to the carbon connected. So this is like alkyl group. Then oxygen is in between. Oxygen can be like electron withdrawing group, electronegative element. Okay. So this carbocation not much resonance stabilized compared to that of this carbocation. This carbocation oxygen can directly give, or through OCH3, or the lone pair can be given to the carbon atom containing positive charge. Therefore, this is the more stable one. If it is the more stable one, then Br should be Br, that is Br minus, should be attached to the carbocation. So get finally CH3O CHBr and CH3. This is the major product, and this is according to Markovnikov's rule. Therefore, option number 2 is wrong. They are given according to anti-Markovnikov. It is not according to anti-Markovnikov's rule. It is according to Markovnikov's rule. Therefore, second one is the wrong statement. Option number 3. Basicity of halides decreases in the order. Okay. Now, HF is an acid. HCl is an acid. HBr is an acid. And HI is also acid. Which is the strongest acid? Strongest acid is the HI. Is the strongest acid. HF is the weakest acid. Okay, right? Because it can easily dissociate to give H plus and I minus. Now reverse way around, basicity of halide decrease in the order. It is correct. Reverse way around. Nucleophilicity is the reverse order. What is nucleophilicity? That means I have got F minus, Cl minus, Br minus, I minus. Okay. Nucleophilicity means it can give electron density to electron deficient compound. Okay, in all these cases. Which can easily give iodide ion, can easily give because it is the most because the least electronegative element. Fluoride cannot give easily electron density because more electronegative. Therefore, reverse order for this. Okay, compared to basicity order. So, option number 3 is also correct. Next one, option number 4. Rate of SN2 reaction is independent of the polarity of the solvent. No, it depends on the polarity. Depends on the polarity, and you require polar aprotic solvents. We require polar aprotic solvent. Therefore, option number 4 is the wrong statement. Last, finally, sigma complex arene ion is a resonance stabilized. What is arene ion? Arene ion is a benzene ring attaching to the electrophile. Suppose it attached electrophile, we get a plus charge. So it is arenium ion. And you know that it can be resonance stabilized. So fourth statement also correct statement. So how many statements are correct here? 2 are wrong statement. Second and fourth is a wrong statement. First statement is correct. Third statement is correct. Fifth statement is correct. Altogether 3 statements are correct. Numerical type question. Therefore, answer should be 3.00. Okay, right? Question number 10. Which of the following statement is incorrect for ethylene dichloride and ethylene dichloride? Okay, so let me read the structure of ethylene chloride. Ethylene dichloride is first structure. Ethylene dichloride is a CH2, single bond CH2. This is a ethylene. Suppose there is a double bond ethylene. Ethylene dichloride. Okay, so it is a Cl is there and there is a Cl. Okay, double bond is removed. This is ethylene dichloride. That is the first compound. And what is the ethylene chloride? Ethylene chloride is CH3, then a CH, 2 chlorine atom, the same carbon atom. So this is a vicinal dihalide. This is a vicinal dihalide. Halogens on the neighboring carbon atom. Here halogens are same carbon atom known as the geminal dihalides. Okay. So option number A. These are structural isomerism. Isomers, correct. Okay. Molecular formula is same, correct. Okay. Structures are different. Both of these yield the same product on reaction the alcoholic KOH. What is the alcoholic KOH? Alcoholic KOH is a dehydrohalogenating agent. Dehydrohalogenating agent. That means you have to carry out elimination reaction. Suppose I carry out elimination. So it remove HCl. How many HCl can be removed? 2. Okay. So on each carbon atom, 1 hydrogen remains. 2 hydrogens removed, 2 chlorines are removed. So there should be triple bond. Okay, so we get ethine here, ethine. Here in this case, remove hydrogen and chlorine from the neighboring carbon atom. Second set, hydrogen and chlorine from the neighboring carbon atom. Therefore, we are left with the CH and CH and triple bond comes. This also ethine. Both give the same product. Statement is correct. Correct statement. Option C. Both these yield the same product on treat the aqueous KOH. Aqueous KOH, K plus and OH minus act as the nucleophile. Cl should be removed. So with the aqueous KOH, we'll get CH2OH, CH2OH. Okay, we get alcohol. So alcoholic groups are there on the neighboring carbon atom. Okay, neighboring carbon atom, and the name of this molecule is the ethylene glycol. Ethylene glycol. Now, what about this case? Okay, what this case? So aqueous KOH is there. So remove halogen atom CH3, then C, H, OH, and OH. Whenever there are 2 OH groups are there on the same carbon atom, so it loses water molecule. Dehydration takes place to give finally CH3. Then CHO will get aldehyde. 2 carbon atom, it is known as ethanol. Ethanol. So they will not give the same product with aqueous KOH. Therefore, option number C is the wrong statement. Last one. Both of these yield the same product on reduction. What is reduction? Reduction means addition of hydrogen or removal of electronegative element like oxygen, chlorine, in general halogen there, chlorine, bromine, iodine. Okay, so what you'll get now? Remove those chlorine atom, introduce hydrogen, so become CH3 and CH3. So both the cases will get ethane as the product. Option number D is the correct statement. So what is the answer? Incorrect statement. We want incorrect statement. The answer is option number C. Okay, right? If you have liked this video, please do subscribe RD Chemistry. And those who are watching for the first time, please do subscribe, share, and like. Thank you.